we can start with the agenda of today. So today we have quite a lot of things to talk about. So it will be quite fast. Well, I mean, I'll try to be fast, but not to be imprecise. So let me know, of course, if you can follow me, if you have any further questions and everything. Of course, if we are not able to finish everything, it's fine. I mean, we also have another laboratory next week, and then the last Friday of the year will be dedicated to a question and answer a couple of hours. So you will be able to come here to let us know, to let us see the code you're working on, which part of the assignment you have already done, and I will also do some more in-depth analysis regarding the moving loads, which will be the last part of the course of the laboratories dedicated to them, and also the optional point on your project. So during the last lecture, we will also be able to go a little bit in depth on what you need to do the assignment. So today we are doing basically 4 things. So actually 5. So we are introducing lumped element. So last time we saw what are how to compute the mass and stiffness matrices for distributed elements. So the same things you saw in classroom. We will see how to introduce concentrated springs, concentrated masses. Then we will see how to model damping. So for now, structural damping, but some of the consideration we did for lumped element will be also used to discuss concentrated damping. And then we will start looking at frequency response functions. So we will see how to use all the frameworks, all the code you have to compute a frequency response function between an input, which is always an harmonic force, and an output, which can be a displacement, an acceleration, a reaction force, or an internal action. So we have those different options, and we will see how to model them. And lastly, we will see how we can also use a modal superposition approach, which reminds me something we've already done in class, I hope. So we will see how to extract the modal characteristic of a structure using FEM, and we will see how the results of the modal approach using FEM and the results of basically the previous point compare one against the other. So all these are points that goes into the assignment, so it's much useful for you. And then finally we'll see something regarding static deflection, so how to compute, which is the deformation of a structure if an external load or its own weight is applied to the structure. So this is basically the agenda of today. We will start with an exercise that we will go that will be followed throughout the lecture to see how to develop it. In this case, we have a structure. The structure has a certain set of parameters. You can see that the structure has several constraints with respect to the ground. So it has a clamp on one side, it has a hinge on node 7, we have a coordinate reference system. But the most complicated part for now, for us, is to model what happens in the right part of the structure. Because as you can see, there is a concentrated mass. So imagine there is a rigid body who has a certain mass and a certain moment of inertia, as well as 2 springs which has a stiffness of Kx and Ky, which are connected to the ground. So our quest for today is how to model those concentrated elements within our structure, because as for now, our code does not allows us to directly input those parameters, because we saw that if we go throughout the script, if we go throughout the input file, there is not a section for concentrated elements. So it's up to you to put and to modify the mass and the stiffness matrix that are the outputs of our code to account for those additional parameters. So the code itself won't do that. It's up to you to go throughout the matrix and see how to modify it. So for now, we start by building the input file. We compute the mass and the stiffness matrices and everything. Then we partition the various, well, actually, then we add the various masses and the various springs inside the matrix that we obtain from the code. Then we partition the matrices exactly as we did before. So we separate the free coordinates and the constraint coordinates in global, the free and the constraint global coordinates. And then we compute the natural frequencies and the mode shapes. Of course, since we have additional parameters, the mass and the stiffness matrices will be modified. If the mass and the stiffness matrices are modified, it means that also the natural frequencies and the mode shapes of our structure will change with respect to case of a free structure with no concentrated masses. For example, if we just add a spring, we shall expect the various natural frequencies to increase because, of course, k is in the numerator of our formula. And conversely, if we had, for example, a concentrated mass in our structure, we shall expect natural frequencies and Helmholtz shapes to lower a little bit their value. So this is just a rule of thumb, but we can also make, if you want to play a little bit with the code, you are of course welcome to make an exercise with concentrated, with and without the various concentrated parameters, and see how the structure changes its behavior if we make these modifications. So we make our input file. You can also of course just copy this from the slides as soon as we upload them, so we can see that we define the various nodes with their degrees of freedom, their constraints, their position. Then we define the various beams with the adjacent nodes that we use to build them, as well as the properties of the materials that we include. And we see that basically, by looking at the structure, we can see that the only modifications we have to do are concentrated on node 5, because node 5 is right now the only one where we have concentrated elements. So we draw the structure, we compute the stiffness matrix, we compute the mass matrix and everything. We know that the structure has basically 16 degrees of freedom plus 5 constraints because it is attached to the ground. So 3 constraints are on node 1. Basically, node 1 is just blocked with respect to its displacement. And 2 constraints on node 7, because node 7 is only allowed to rotate a little bit. And the matrix will obtain as sparse, and we can just run the code and obtain everything exactly as we did last time. However, when we want to add the various concentrated mass, we need actually to first define which are the degrees of freedom which are affected by this addition, and then to use the various outputs of our previous functions to know, to understand where to place those additional parameters. So we know that the concentrated mass there is applied on node 5. So if you remember from last theory lecture of Professor Zasso, we know that the mass matrix and the stiffness matrix can be added together. So we know that the total mass contribution, those coordinates, will be the mass contribution of just the structure. So imagining that we have a beam, and we imagine having we imagine giving to node 5 a unitary acceleration in its 3 free coordinates, and we know that that will be the basis that our code outputs to you. And if we want also to take into account the addition of a mass, we'll have to know that if we give to that specific point a unitary acceleration in each of its 3 coordinates, we shall expect an additional inertial term, which is exactly the mass we have to the structure. So what we have to do is that we have to sum in the various degrees of freedom which are affected by the movement of that mass, an additional term, which is the mass or the moment of inertia of the free body, of the rigid body, which is attached to that node. Is it clear? So we just have to add 3 terms in our mass matrix. Which are the terms on the mass matrix that we have to modify? We can use our EDD matrix. The EDD matrix, remember, is the matrix that links the various nodes to the global degrees of freedom that are affected, that they are converted to when we assemble the various matrices. And we know that on the 3 terms of which are affected by the movement of node 5, we have to sum the contribution of the mass matrix of a free element. We know that the mass matrix of a concentrated body has just 3 terms, so 1 for its vertical, 1 for its horizontal displacement, and 1 for its rotation. So we have just M and J, because those are the 3 degrees of freedom of a body. We know that the horizontal degree of freedom of that rigid body will correspond to the horizontal displacement of node 5, which correspond to the 10th row and 10th column of our mass matrix. We know that the vertical displacement of the rigid body will coincide with the vertical displacement of node 5, in this case, the 11th global coordinate of our structure, and its rotation to the 12th. So in this case, we add the various terms which are contained in the mass matrix directly to those terms. I know that with Professor Zasso, you also saw how to use the extraction matrix, so a matrix who has the various number is a rectangular matrix who has dimension, which has dimension of the various global coordinates on the rows or columns, depending on how you rotate it or on how you transpose it, and on the columns or the rows, the various degrees of freedom of the nodes or the coordinate or the element you are trying to add the various quantities to. We can use basically the same approach by using the structure matrix, only in this case it is just faster not to create that very big matrix every time we want to add a certain element, but we just go to the global stiffness matrix and we have those terms there. So for us, it's very easy. We also have the code. It's just 3 lines. We go to the matrix, we find which are the elements, we create the mass matrix, and then we sum the global mass matrix to the parts of the global mass matrix which correspond to those degrees of freedom. For the springs, basically the same approach. We know that those springs are connected to the ground, and on the other side they are connected to node 5. So we know that since the stiffness matrix, each element of the stiffness matrix corresponds to a force in that specific global coordinates, which is equal to a unitary displacement of that specific coordinate in the global reference system. We know that if we attach a spring to node 5, and we know that node 5, for example, moves horizontally or vertically, its stiffness contribution will be equal to the stiffness contribution of the structure as you computed before, plus an additional stiffness contribution, which is the spring that we want to attach. So we go to, again, our linear matrix. We know that the vertical and the horizontal displacement of node 5 are the 10th and 11th global coordinate. So to each of the elements corresponding to the 10th row and 10th column of the global stiffness matrix, we add an additional stiffness which corresponds to the stiffness of our spring. So right now, quite easy, not in particular. We just have to add those elements. And remember that we have to add those elements only on the diagonal of our matrix, because the diagonal of the mass and the stiffness matrix correspond to movement of those specific coordinates and forces which are felt by those specific coordinates. Things change a little bit. Well, sorry, we also have the additional code. I always forget about this. Things change a little bit if we want to implement a concentrated mass between 2 elements, 2 nodes of the structure. Because in this case, it's not true that we can just sum those stiffness contribution on the diagonal or mass contribution to the diagonal, or stiffness, because mass is never placed between 2 points, but we can never add, only add a stiffness contribution on the diagonal of the stiffness matrix, because in this case, we have to create a workaround based on the fact that if there is a relative displacement between node 2 and node 5, that will affect the global stiffness of our structure. So we won't have only contribution on diagonal, but we will also have 2 extra diagonal terms corresponding to the relative displacement of node 2 with respect to node 6, and vice versa. So what we can do to implement a spring, an internal spring in our structure, is to remember which is the contribution of the potential energy of our, sorry, let me move a little bit the chart, because I'm not seeing anything. So we can remember which is the global contribution of the potential energy to the potential energy of the movement of that specific spring, so in its local coordinates, because we know that we can treat that spring as basically a cable, because basically a spring is just a cable with a very, very, very low stiffness. So we know how to write the stiffness, how we can write the potential energy of a cable element by using as inputs the various displacement of its extremities. So we can, by creating a vector which contains the various movement of that specific element in local coordinates, we can rewrite, the potential energy of that specific cable, of that specific spring element in its local coordinates. So we know that it will be a 6 by 6 matrix, which will be very sparse, because the only contribution to the potential energy of a spring will be a relative displacement of the 2 extremities in its longitudinal direction, because any lateral movement will not affect the global potential energy of that specific element, if, of course, the displacements are very small. So we can create a 6 by 6 matrix which allows us to write the potential energy in local coordinates. Then, since we know that this element is actually not written in global coordinates because there is a relative rotation between those two elements, we have to return from the expression of the potential energy in local coordinates to the expression of the potential energy in global coordinates. So we have to rotate the various degrees of freedom because the movement of, for example, the coordinates of node 2 in global coordinate will affect both its longitudinal and its lateral displacement. So we have to take into account that by using a rotational matrix. Actually, in this case, two different rotational matrices which will create basically a 6 by 6 matrix. So we can assemble the various rotation matrices into the expression of our potential energy to write the potential energy of that specific element or spring element in global coordinates. Then, by using, again, our ADB matrix, we can create an extraction matrix. So in this case, actually, it's a little easier to use the extraction matrix to create basically two very sparse matrices which will have 21 rows, because we have 21 nodes, 21 coordinates in our global reference system, and 6 columns, so that we can assemble our potential energy to the global stiffness matrix of our structure, and then the contribution of that spring in the global coordinates of our structure will be a 21 by 21 matrix, with a lot of zeros, and some terms in the specific global coordinates which are affected by the movement of that node, those nodes. So, if you think about it, it's a block scheme. So, you have the extraction matrix, you have the rotation matrix, you have the potential energy matrix of that specific, you have the stiffness matrix of that specific element in its local coordinates, and then again, two other matrices which are just transposed to return into the global coordinates. So, and then in the end, we just sum the new stiffness matrix of that specific spring in the global coordinates of our structure, the stiffness matrix you just obtained from your computations. So, it might be a little complicated if you look at it at first, but remember, it's just a matter of iterating a series of calculations. We know the stiffness, the expression of the stiffness matrix of an element in global coordinates, because it's just a spring. We know how to pass from the local reference system to the global reference system. We know how to pass from the local coordinates to the global coordinates. So it's just a matter of translating your operation many times until you can just sum it to the global stiffness matrix. So we can do this for springs. We can also do it for dampers, but in this case, then all the hypotheses of damping that you made at lectures becomes basically invalid. So you have to solve the movement problem of our structure numerically, because you are not able to do it with the modern approach of all the various tools we saw together. But the possibility, the framework you can use to make all those various elements talk to each other is just always the same. Okay. You also have the code, so it's just a matter of taking all these expressions, remembering which are the nodes at which you decide to attach springs, and then all the computations will just be done by the code for you. So the only thing you have to remember is that right now the code does not give you the angle of the between the local and the global coordinate system for the case of the spring, so you have to work that out yourselves. But other than that, it's just a matter of applying those lines of code in a 4-cycle for all the springs you want to introduce to the structure. Of course, in the end, if we do all our various computations, if we include the concentrated elements, if we include the concentrated springs, the concentrated masses, we will end up with a matrix which is modified with respect to the original matrix we started from, but also in this case we can partition it, then we can obtain the movement, so we can obtain the eigenvalues and the eigenvectors of the free part of the structure, but later during the classroom, during our classrooms, we will also see how to use the partition of those matrices to find additional terms and additional variables, additional non-quantities for our structure. And then we will see if you want to make a comparison between the three solutions, so without any concentrated mass and concentrated stiffnesses, and the results you get from these additions you are most welcome to. So remember that you have to look at, you have to choose a proper normalization of the various modes, otherwise we will just compare two things which are completely unrelated one with respect to each other. So be wise in your normalization, and then you will be able to see which are the effects of the addition of these various elements. Okay, is everything clear right now? I mean, I went a little fast, so I hope it did not terrorize you. But, okay, I'm not seeing any very angry faces, so I will take this as a yes. Okay, so second part of this lecture is damping. So right now, our code allows you to compute the mass and the stiffness matrices of a structure. What about the damping? Because remember, damping is important, because otherwise, as soon as you go into resonance, all the amplitudes just skyrocket, which is not nice as a structural engineer. So whenever you are modeling a structure, we have to take into account that there is some damping in our structure. For this case, we use a fairly smaller example. So we have just a beam with 30 nodes. You have all the various parameters. We decide to model this structure in our FEM. So we create the mass matrix, we create the stiffness matrix, and so on and so forth. But for what account damping, we have to take into account the Rayleigh hypothesis in order to properly introduce it. We know that, I think you did it in classrooms with Professor Zasso, but also in other courses during your bachelor, that for under specific requirements, it is possible to write the damping matrix of a fairly large structure as a weighted sum of its potential, of its stiffness and its mass matrices. And the nice approach about that is that if we are able to diagonalize the mass and the stiffness matrices, we are able to do so with a linear combination, which is wise, because then we can use the model approach, we can use a number of unknowns of degrees of freedom of a structure, and then we are able to solve it numerically much faster than if we have a non-diagonal matrix. So in this case, what we use are the dimensional damping ratios of certain numbers of mode shapes of modes that we obtain, for example, experimentally, for example, numerically, for example, under a certain set of hypotheses, and we use those parameters to solve a linear system whose outputs are the parameters alpha and beta, which are the weights with which we sum the mass and the stiffness matrix. So we can use the same approach also in FEM. Remember that sometimes we will be able to find precise values for those parameters because they are, if we have, for example, two-dimensional damping ratios, it's quite easy to find them. Sometimes we might be forced not to find exact values for those parameters, but to use a least square approximation, because maybe we have the dimensional damping ratios of several mode shapes that, for example, you obtain in an experimental campaign. So let's say you take your helmet, you go into the field, you put out of accelerometers on a structure. We use all the model identification techniques that you learn in the first part of the model characterization laboratories. We find all the dimensional damping ratios of your structure. You try to make a FEM model of your structure, and you want to use the Rayleigh hypothesis. So we have all the dimensional damping ratios, and then we try to minimize the parameters alpha and beta so that they create a reasonable, good enough approximation of the damping of your real structure. So this is always what you do in the field. So you make measurements, you make an approximation, you find those values, and then you use them in the FEM, and then of course you compare. For example, but this is another point. You will compare the results of your FEM code to the results of your real structure to see whether your approximation was good enough or was completely bullshit. When I do it in the field, usually it's bullshit, but I hope that for you it will be a little better. So again, damping ratios, minimization of the problem, you create the matrix, you extract the parameters, and then you are able to write the damping matrix as the weighted sum of matrix K and matrix M. So this works basically kind of flawlessly. Remember that in your assignment you will receive, if I'm not mistaken, you will already have the values of coefficient alpha and beta or of the various mode shapes of the structure. So you can obtain those parameters, and then you can create the damping matrix of your structure. So solving a linear system, finding parameters, summing them, and creating the damping matrix. Okay, was that clear? Was that super fast? Okay, again, not seeing any people angry, so I'll take it as a yes. let's go into a more tough part of the lecture of today, which is the frequency response function of a structure. So, what is the frequency response function for general mechanical system? So, does anybody want to answer? Okay, if not, remember that sometimes we are not interested in finding the free response of a structure, which is the one we can compute. We already know how to compute, but we want to see which is the output response of a structure based on an input that we decide to give to it, which can be, for example, a harmonic load, maybe the movement of a piece of machinery, can be the wind, can be any possible external load or movement of a constraint which is applied to our structure. And we want to know which is based on the amplitude and the frequency of the input we give to the structure. We want to know which will be the output of our structure in several different nodes. In this case, we use a very small example, which is, again, a beam. Actually, it's the same beam that we did before. So, 30 nodes, a certain set of geometrical and physical parameters, and we decided to give to our structure a certain input, which is a concentrated force with a known value, which is like 0, and a certain amplitude, which will change in the range between 0 and 500 Hz. And the goal we have for this part of our lecture is to find a way to compute the frequency response function of various nodes in this structure based on the input that you give to the structure. So basically, transfer function, force goes in, displacement or rotation or acceleration goes out. So, how to do this? We return to our partition matrix. Don't be scared by this slide. It's not something. It's not as bad as you as it seems. So remember that in the first part we have the output of the previous part of our lecture. We have a mass, a stiffness, a damping, and a stiffness matrices. We have a set of global coordinates which are already partitioned between the free and the constraint coordinate. And then on the other side of the equal, we have the various forces which are applied on the global coordinate of our structure, plus the reaction force in case of the constraint coordinate. We know that in one of the rows corresponding to FF, our input will go in, because that is the external force which is applied on a specific coordinates. We also know that the values of xc, of x dot c, and x dot c will be equal to 0, because we know that they are constraint coordinates, so they cannot move. The value will always be equal to 0. So in a way, it is possible to rewrite this problem by separating the first part, so the part where we have the free and constraint coordinate, where we have only the free coordinates, so the first row down there, with the problem where we want to obtain the forces of the constraint coordinate. So it is a system of equations. We are able to divide them in two. So on one side we have the unknowns are the free coordinates. On the other side, the unknown are the reaction forces. We also know that since the movement, the displacement, the velocity, and the acceleration of the constraint nodes are always equal to 0, it is possible to remove all the rectangular parts, so KFC as well as CFC as well as MFC. All those matrices are multiplied by vectors which are always equal to 0, so we can just get rid of them. And the results we get is a system with only the free part of the various matrices, the free coordinates as our unknown quantities, and the vector of external forces applied to the various global coordinates as our inputs. All the rest, you can just get rid of it, or actually better. We will return to the other parts of this matrix once we will want to compute the reaction forces applied to the various nodes. So it's only a matter of partitioning the matrices so that, and remembering that the constraint nodes will not move, so that we can just get rid of them and obtain a much smaller system. Then we write the input vector to that problem, because remember, we know which are the forces applied to the various global coordinates, because those are the inputs of our problem, and the outputs are the values of xf, so the free coordinates over time. We know also that the external force is only applied to the vertical displacement of node 7, and thanks to our IDB matrix, we know that the vertical displacement of node 7 corresponds to the 18th row of our free vector. So the input vector of our structure will be a vector with a lot of zeros, save for the 18th row, which corresponds to the vertical displacement of the middle node of our structure. That is our input. Then we want to obtain, of course, the output. And for that, we use exactly the same approach of what we saw, for example, during mechanical vibrazioni, during the first year if you did your bachelor year, or any course of vibration analysis in any other university. We remember that since we created a system with n degrees of freedom, it is always possible to use the superposition principle and all the various mathematics behind it to say that if we have we want to solve a system of equations of motion, those equations are differential equations, so we can impose a solution, general solution shape, which will have the same frequency of our input force that we know because we decide which is the force, the frequency span of our force input. So we can impose a general solution shape to our vector of free coordinates. We can derive it 2 times and then create the denominator that we already saw during other courses. So basically, same expression, but in this case, we arrived to it using FEM. During other courses, we arrived there by making different computations by creating the matrices by hand. So we can obtain what we call basically the frequency response matrix, the frequency response function matrix. So a matrix of terms which depends both from the position in the matrix as well as the frequency at which we are computing, we are making that computation. Because remember that by looking at the expression, if we change the value of omega, the value of the various terms inside that matrix will change because we are multiplying different matrices for a term will change depending on the frequency. So in order to make this computation, we will have to go throughout our frequency vector and compute the various terms in the frequency in the frequency response function matrix along each frequency. So we will create in a way a vector of matrices or a matrix of vectors depending on how you want to look at it. But the general idea is always the same. For each frequency we make that computation, we create our frequency response function matrix, which gives you as a output. Basically, if we multiply that function for the unknown, or actually for the known force vector, you get the relative amplitude, which, remember, is a complex number. So each of the terms inside that matrix have a modulus and a phase. So they are not just real quantities. They can have a relative modulus and a relative phase, and are multiplied by the input force, and they will give us as an output the relative amplitude and the relative phase between our input force and the displacement of the various degrees of freedom. So exactly as we did in other courses, or in this case, we arrived to it by using first creating those matrices using FEM, and then by multiplying them for our unknown force vector. Sorry, for the group of people up there, may I ask you to lower a little bit your voice, because it's a little annoying. Thanks. So, returning to our code, we are able to get these functions. Remember that those are the output vector. The output of that computation is a vector of complex numbers, and each of them corresponds to the relative movement of any of the various degrees of freedom of the structure with respect to our input force. If we want to look at a specific degree of freedom, we use again our EDB matrix. I told you that those matrices will return many times. So for example, say we want to know the vertical displacement of node 5, we go to the EDB matrix. We know that the vertical displacement of node 4 corresponds to the 9th row on our vector of free coordinates. So we take the matrix, we take our frequency response function matrix, we multiply it for the vector of external forces, and we get then we compute the module and the phase of that specific number, and for each of the frequency, we compute the amplitude, the relative amplitude and the phase between an input force and an output displacement. So we translate, so remember those terms have a unit of measurements because they are meters over Newton. So we give 1 Newton of force, we shall expect a movement of 1 meter. We give 10,000 Newton of force, we shall expect a movement of 10,000 meters. So remember, you always have to scale it for the magnitude of the force you give to our structure. But as soon as we run the computation, and as you can see, the script is very easy. We just have to make this computation many times and iterate along our frequency vector. Then we are able to create the magnitude and phase plots of our frequency response functions. So, exactly as we did in other courses, in this case, it's automatic, so you just have to run the script and compute the various terms per each of the frequencies. But as you see, the mathematics which are behind it are basically exactly the same you saw before in classrooms, are exactly the same math that you were using in the analytical part of the course, only it's not you that do the calculations, it's your MATLAB that iterates on the frequency vector. So, that is quite easy. Displacement against force frequency response function, but maybe you are not interested in the displacement. Maybe you are interested in knowing which is the acceleration of any of the 3 coordinates you get, any of the 3 coordinates you want to investigate. How do we get from the displacement frequency response function to the acceleration frequency response function? You have to remember that in the frequency realm, the acceleration is just the displacement multiplied by omega squared. So we have already have the frequency response function matrix of the displacement of the various 3 coordinates. You can compute the frequency response function that links force to the acceleration of the various nodes by multiplying it for minus omega squared. So you will get a matrix. Each of the terms will be multiplied by a term which is minus omega squared at that specific omega. Then you get then you will multiply it for the forcing vector of forces, and then you will get what we call the accelerants of the various nodes. So again, the script is very easy. We just run a force cycle along the length of our frequency vector. We compute the various terms, then we assemble them into vector or into matrices, and then, depending on the coordinate you plot, you just extract from those vectors, from those matrices, the quantities you are interested in, and then you plot them against frequency. So in this case, we can compute displacement against force for each frequency. We can plot acceleration against force for each of the various frequencies, and then you're able to get a quantitative response of your structure. If I can give you a small hint, if you want to play a little bit with it, try if you already know which the various mode shapes of a beam will be, you can try to see which is the frequency response function on different points of the beam and compare this to the mode shapes and the natural frequencies of a beam. For example, if we compute the frequency response function of a point at midspan, we shall expect to have a maximum value whenever in the frequency range we go near all the odd mode shapes. For example, if we go close to the even mode shapes, we shall expect the relative amplitude between the link between the input force and the output displacement to be very slow, to be very small, because we are close to a point close to a frequency where that specific part of the structure is not moving, even if we give a very high force in that specific part. Or we can also look at the cross frequency response function. So what happens in a specific node if you give an output in another node? So this is usually also something we can investigate together during the oral, because some structure at some frequency show a very strong correlation between, for example, an input at midspan and an output, for example, at quarter span. But for some mode shapes where either that the point in Z-span or the point at quarter span are in a node, at those specific frequency, you will expect to have a very low magnitude. So you are, of course, most welcome to play with the code, to play with different points, and to see whether the output of your code corresponds to what you should expect based on your theory lessons, based on your sensitivity. Also, is a nice way to check whether the results of your code are correct. Well, no, usually they are correct. I hope that for you, but in case you can use those tricks to see whether you have problems or not. Okay, so maybe you are not interested in computing the frequency response function of just a displacement or an acceleration. Maybe you are doing a structural analysis, so you want to know which is the link between an input force and, let's say, the internal actions on your structure. So, if you remember, we are working with a discrete system because we decided to pass from the general set of infinite coordinates, the system expressed as a series of partial differential equations, to a system where we discretized our structure, and we already know which are the global displacement of the various nodes. So how can we go back to the behavior of the structure within two different nodes? So we know that we're able to express the displacement of a node using the shape functions. We know that the shape functions depend on a set of polynomials, and the coefficients of those polynomials depend on the relative position of the various extremity nodes, plus what we call the running coordinate, so that xi parameter that we use to run throughout the length of the element. So we know we can compute parameters A, parameter B, and C, and in case we want to look at the transversal displacement based on the relative position and the relative displacement of the nodes. Then we multiply and we express those displacement as a product of two different vectors. So the vector of the global coordinates of the neighboring nodes of the element plus the vector of those coefficients evaluated at different values of parameter xi, and then we're able to get a vector of horizontal and vertical displacement of our element. If we remember how we passed from the expression from our single beam element and its running coordinate to the mass and the stiffness matrices that we were able to assemble into our code, you remember that we used a framework which was the Euler-Bernoulli beam theory. So we know that we can express the longitudinal action along beam as well as its bending moment as well as its shear force as a function of the various first, second, and third derivative of longitudinal, transversal, and transversal displacement with respect to the running coordinate. So in the first part, when we were creating mass and stiffness matrices, we went from the Euler-Bernoulli formulation to the mass and stiffness matrices. In this case, we're going backwards. So we solved the problem, we found the values of the free coordinates. Now, we remember how we wrote those interactions. In this case, we know the values of the various parameters for which we multiply our running coordinate, because we got them from the solution of our problem. We derive those expressions that now are known because you know which are the various parameters, and then you get the values of n, t, and m as a function of your running coordinate and as a function of the relative displacement of the various nodes. So this again is a chain of thought. So we solve the problem, find the values of the free coordinates, then use the values of the free coordinates to compute the parameters A, B, C, and D of the shape functions of your beams. We use those values, the values of the derivation of the shape functions of the beam to express the interactions, and then we get back and we find basically what we were looking for. So in this case, we just remember that for each of our beam elements, n just depends on n is constant, because it depends on the first derivative of the longitudinal of of the longitudinal displacement of our beam, which is always the difference between the longitudinal displacement of the various nodes. So its derivative will be constant. So basically, n is constant and only depends on the derivation of its longitudinal displacement. So that is quite easy to compute. For the transversal displacement, however, the polynomial was bigger, so we were able to compute the various functions as functions of the nodal displacement. So with the item, we find an expression of the second and the third derivative that, if you think about it, it only depends on xi and the various parameters, and the nodal coordinates, and then we assemble everything to create, to express internal actions as a function of a product of our shape functions and their derivation, which now are much easier, times the nodal displacement of the nodes which neighbor each of the elements. So I know we are just going very fast throughout the mathematics which are behind it, but I trust that you did them with Professor Jasso, who went much more in depth regarding those, so we can just we're just seeing how we can implement all those things in a code, and basically that's what we did. That's what we did. So let's look through this code together. So we want to find the internal action of element 11, which is the element between node 11 and node 12. So we find the degrees of freedom which are associated with the two nodes 11 and 12, which neighbor that specific element. So basically we know, we find those values, we compute which are the coordinates and the relative displacement, or actually, sorry, the frequency response functions of node 11 and node 12. So each of the two nodes will have three different, one horizontal, one vertical displacement, as well as a rotation, and you are able to extract them from the computations we did before, so from the extraction of the frequency response function matrix. So those terms are known because we computed them before. Then we know that we want to compute, in this case, the internal actions very close to the end of element 11. So we can just assume that xc, so our running coordinate, is very close to the end of the element. So in this case, we just assume to be equal to the length of the element, but you can always just click a little bit that parameter xc to see what happens within the various terms, within the various points along our element. So we compute our parameters c and d, because as you see, parameter c, this expression, the two expressions of parameter c and parameters d, are just the translation of these terms using the true values of the c coordinate of the running coordinates, in this case, which is equal to f. So those terms just are computed, while the term for which we multiply those terms, so the values of the nodal displacement in local coordinates, are just what we extracted from the initial matrix. In case we have a rotated element or any change of coordinate system, we have to use rotation matrices, but in this case we are just on a line, so we can just use directly the global coordinates. So these terms, we compute them based on c, and these are values c and d, and then we just assemble them. And finally, we compute the bending moment and the shear action by multiplying the two terms that we computed based on the value of the running coordinates and the value of the displacement of the various nodes in global coordinates, and then we find an extraction of MA and TA as functions of the parameters we computed before. Remember that those parameters change depending on the frequency, because those are the outputs of a frequency response function. So what you have to do is iterate the cycle for each of the frequencies you want to investigate, and for each of the frequencies, you will compute the relative displacement of the nodes. You will use the relative displacement for the nodes, which, remember, has a modulus and a phase, so those are all complex quantities along the computation. We use the relative displacement of the nodes and the shape functions to find parameters C and D. We use the expression of the Euler Bernoulli theory to find the bending moment and the shear force as a function of the combination of nodal displacement and shape functions. Then we obtain those two values, which are complex quantities. So we iterate across each of the frequency, and then you get something resembling this. This is the frequency response function between an input force, which is the force always applied at node 7. So same output that we did before, same input we considered before, but in this case, the output of the frequency response function are again forces. So in this case, this frequency response function has no unit of measurements because they are forces over forces, and they have a module and a phase depending on the frequency we are computing it. So we shall expect, in some cases, to have very high forces, even if the action, the input on the structure is very small. For example, if we are close to resonance in some specific conditions, we will have very big nodal displacement, and so we'll have very big internal forces. And this can be a problem because, for example, if we have a very long bridge and the bridge enters resonance, even if we are giving to the bridge a very, very small external input force, the displacement of the bridge will be very high, and so the forces that the various elements of the bridge experience will be very high. And if you want to dimension those elements in your code, or because maybe one day you will go out and be engineers and design bridges, you will have to take into account that at some frequencies, even if nominally the bridge should be able to hold all the weight without problems, we might have an amplification of the internal action, which is so high that then you have failure, which is not something I like you to discover. So remember that you can use this framework to look at the various effect of external actions onto the internal forces that our structure experiences. And if we want to go a little out of the content of this lecture, we can use those internal actions as input of the structural dimensioning of our structure. So we go full circle, we dimension the structure, we find the parameters, and we iterate again to find which are the new resistance parameters. So again, I know it might feel a little overwhelming because we saw a lot of matrices, we saw a lot of iterations, a lot of computations, but consider that we are just going passage by passage along exactly the same computations you did during theory classes. If you remember, when we were solving structures using partial differential equations, you were computing the frequency response function. In this case, you were not working with finite element method, but you were working directly with the mode shapes. But if you remember, the calculations are exactly the same. Only in this case, we are doing them not by hand, but with a computer who can go throughout all these elements and compute the frequency response function, maybe also of a very big structure. So theoretically, is not any different from what we did already in classes. It's only applied to bigger structures. So, and again, this is just a short mention of example of what we discussed before. So sometimes the global reference systems and the local reference system coincide, but remember that internal actions are always in the local reference system because running coordinates are always along length of each of the elements. So sometimes you have, for example, you may have an inclined element. If you remember in the assignment, you will have some elements which are inclined. So if you want to pass from the global reference system and the various outputs of our frequency response function to the internal actions on an inclined element, you will have to use the rotation matrix of that specific element, but luckily in this case we have the angle of each of the elements, so we use the angle which is contained in one of the output of the load structure function to compute the rotation matrix of that specific element. We pass from the global coordinates to the local coordinates, and there we can compute the coordinates and displacement of the extremities of each of the nodes in local coordinates. Then as soon as we have the displacement of the nodes in local coordinate, we go to through our shape functions, through our Euler-Bernoulli formations, and we get the internal actions. So again, Input force, frequency response function matrix, output displacement. If you want to have the acceleration, we derive it and we find the acceleras. If you want to compute the internal actions, then we go through the order reformulation through the shape functions, and then we get output force. So always a chain of blocks of matrices and operations. Okay, is everything clear for now? Okay, is everything a little bit clear? Okay, better, thanks. So again, that's why some of you came before asking whether working on the values, small exercise we did at the end of each classroom can be useful. Again, one thing is to do this on your assignment project immediately. Another thing is to start with a very small structure, play with it, junior code with it, learn what the various parts of the code do, and then use all those knowledge to work on the final assignment. So I strongly encourage you playing a little bit with the various elements of the code to find how they work before starting doing the assignment. Okay, last thing we have to do for what concerns frequency response function is to find what happens when we want to obtain the reaction forces of your structure. And in this case, we have to remember, we have to go back to a partitioning of our matrices to find what happened to the discarded part of the solution that we decided to completely ignore. So, if you remember, when we decided to partition the matrix, we decided to make a big assumption, which was that the constraint coordinate would never move. And thanks to that assumption, we were able to discard a very big part of all the elements which are in the free part of the division of our system, because we said that in the first row of the second system, you remember that MFC as well as CFC as well as KFC all were multiplied by terms which were equal to 0. So we could discard them and we could get a matrix which was relating the input force, which was, again, our input, so a known quantity, so a thing that we use to find the frequency response function, and so on and so forth. But in any case, a quantity that we use to find which is the value of CF. So we can assume that at the end of all the things we did before, we know for each of the input forces, which is the displacement of all the free nodes. And with that knowledge, let's start looking at the second row of the matrix. If you look at the second row of the matrix, we see that there is a term which is MCF, so the transposed of the rectangular matrix that we ignored at the beginning, which is now multiplied by XF double dot, which now is a quantity that we know because we computed it before. Then we have MCC, which is multiplied by XC. And again, XC is the value of the displacement of the constraint nodes, and we know that the displacement of the constraint nodes is equal to 0. Then we have CCF, which is a rectangular matrix, a rectangular damping matrix, multiplied by a quantity that we know. Then we have CCC, again, multiplied by a quantity which is 0. And finally, we have two parts of the stiffness matrices. One which goes away because the displacement of the node is, of the constraint nodes is equal to 0. One which is multiplied by a vector that we know. So, my questions for you is, which is the only unknown in the second row of that system? Once we solve the first part, the only unknown are reaction forces. So, in a way, when we solve the frequency response function problem for the free nodes, then we get all the ingredients that we need to solve the second part of the problem. Because remember that we always have two unknowns in a dynamic system. One set of unknowns are the displacement of the free coordinates, and the second set of unknowns are the reaction forces on the constrained one. Because if the constrained one cannot move, there is a force there. If the free one can move, it means that there is not an external force there. Or if there is an external force, that external force is an input. So we gather all the various pieces. So we use the output of a frequency response function to find the values of all that terms, and then it's just a matter of substituting the value of x0 inside the second part of the matrices, and remembering that the derivation of x of the value of x0 is just minus I, is just I omega times that values. So we can do exactly the same things that we did before and find an expression for the reaction force, for the reaction forces, which uses the CF part of our matrices to find the value of the external forces as a function of the free coordinates, which are a function of the input force. So in a way, okay, apparently there is, there is a so ideally we have, so let me just move the, okay, I will have to stop sharing. Sorry, hybrid lectures can be quite tough from the point of view of having to move between desks. So the external force, we can use it by solving this problem. So basically, we use this expression to find a relationship between x0 as a function of the external forces, and then we use this knowledge to know that the vector of external forces is just minus omega squared plus I omega C CF plus K CF times x0, which is a function of f0. So input force, output displacement, input displacement, output reaction forces. Those are rectangular matrices, so they have, but in this case, this doesn't matter because we are not trying to solve a problem here. We are just straightforward computing the solution. So this is not even a matter of derivation or anything. It's just you plug in your results and you find the reaction forces. And then remember that since this quantity was a complex one, this quantity is a complex one, this quantity again is a complex quantity, and so also the reaction forces will be a vector of, or matrix of complex values, depending on the frequency at which we make this computation and the input force that we decide to give. So those will be a ratio between an input force and an output force, and you will be able to plot the module and the phase of all the reaction forces as a function of the initial quantities, sorry, of the initial forces. Let me share the screen again. So, sorry, my bad. Okay, here we are. So, in this case, we decided to plot which is the value of the vertical force on the left part of the structure as a function of the force applied on the center span of the beam. You will see that if we go very, very close to the to zero frequency, so the starting part, basically that force will be, if you look at the values, if you make all the computations, you will see that that value is 0.5, because if you think about it, we're just giving a force in a vertical direction and we're seeing half of the force on one side, half of the force on the other side. If we go through some of the vibration modes, that force will amplify a lot. If we go through some of the other vibration modes, that force will decrease a lot, because at some frequencies, the structure in a way is absorbing all the external forces, is damping out the external excitation. At some other frequency, it's amplifying a lot. So you have to take that into account when you design a structure or a bridge or whatever you are trying to design. Moreover, let's look at another thing, and I won't tell you which is the answer, but if you want to, if you already looked at it and you want to answer, you are most welcome. Why are not we beginning with a zero phase, but are we beginning with a minus pi, with a plus pi phase at zero frequency? Because why our force should be negative? Because if you remember, this is an amplitude phase diagram, so amplitude is always a positive value, and the eventual sign is multi-sided phase number. And why should we have a negative, 180 degrees phase at zero frequency if we just give a positive force to our structure? Let's try looking at it. If anybody has an answer, you're most welcome to interrupt me. Otherwise, we can discuss about it at the end of the lecture. But keep that in mind when you do your assignments. Okay, so sorry, my bad, I got lost in slides. So the last thing I wanted to, almost the last thing I wanted to discuss with you was how we can use the same tools that we developed before. So the model superposition approach using finite element analysis. Again, for now we use the same structure the same structure we did before, with the same damping values for Rayleigh and so on and so forth. But let's try talk like engineers. We already saw that the finite element methods allow you to model a structure even if it's very complex. Why should we use anything related to the model approach also for working with the finite, also even if we work with the finite element method? And for that, I can just make you an example. Let's imagine that you are designing a skyscraper or the Messina Bridge or any possible structure that you want to investigate. And you make your finite element model, and at the end of the discretization, your finite element model has 100,000 degrees of freedom. So you want to discuss which is the value of, let's imagine that this is a very big bridge. We want to know which is the relationship between an input in force 7 and an output in vertical displacement in node 4 using our FEM approach. So we want to compute this for in a certain frequency range. So we take our discretization, we have a matrix, a stiffness matrix, which is 300,000 times 300,000, and so on and so forth. And so we want to integrate those equations over time. So you ask your MATLAB computer to solve a system of 300,000 times 300,000 ordinary differential equations. Your computer starts working now, and maybe in a million years you will have the frequency response function of your structure. Because as those problems scales with the dimension of the matrices, so if we increase the dimension of the problem a lot, because it's a big structure or because you want to do a very big analysis, or you are not very wise when making your mesh, you end up with a problem which takes maybe a couple of days to a couple of million years to be solved. And in those cases, it is very wise to try reducing the dimension of your problem, because maybe you are not interested in the frequency range of the 2 kilometers bridge between 0 and 1 billion hertz. Maybe you are just interested in its first 3, 4 mode shapes. Anyway, if you remember that we have a language that we can use to express the movement of that bridge using the first 3 to 4 mode shapes, the sum of its 3 to 4 mode shapes, to express with a satisfactory precision its displacement in the frequency range you're interested in, then you pass from a 300,000 system of ordinary differential equation to a system of 3 ordinary differential equations. And the difference in the computational power you ask and the interpretation of the analysis you need is huge, because you can scale your problem by order of magnitude. So even if we work with FEM, even if FEM is already a simplification of your structure, using a model approach in FEM allows you to simplify the problem even more by looking only at the specific frequency range and the mode shapes at the specific frequency range you're interested in, and using the language of the mode shapes to reduce the dimension of your problem and to express the displacement of your structure as the weighted sum of shapes, so only the mode shapes you're interested in. And this is very useful, especially when you have very big structure or very small frequency ranges. So, again, in this case, we use the FEM approach, so we already know how to do all these kind of things. We already know how to compute the frequency response function matrix of our structure, but we also know that if the problem is well posed, if there are no weird dampers around, it is always possible to find a specific reference system within our structure, which is a reference system of the mode shapes, and pass from the physical coordinates of our structure, so the vector of x, to the vector of modal coordinates of the structure, so the vector of q. And we know that the vector of q between the passage matrix between those two reference systems is usually a square, but rectangular, and we see why, matrix containing the values of our mode shapes. So by using those matrices, we can create the matrix of the mass, the stiffness, and the damping matrix in modal coordinates. Those matrices will be diagonal, because that's a property of the mode shapes. If they are well posed, if there are no weird addition to the structure, those matrices will be, more generally, will be squared. And of course, we can also pass from the force, the external force vector, to the generalized force vector in modal coordinates. But the nice thing about this is that we don't need to use all the mode shapes to describe the structure, because usually the matrix Q, the matrix phi, so the passage matrix between the physical coordinates and the modal coordinates is square. But if you want to use only, for example, the first three vibration mode to express the behavior of your structure, you can just use a rectangular matrix who has the first three mode shapes for all the physical coordinates. So the nice thing about this approach is that we can set, and in this case we are setting it for all the first three mode shapes. That's why it's important to sort them properly when you compute them. We can sort and find a passage matrix which is rectangular. We multiply the passage matrix, the phi matrix, and its transpose for the mass stiffness and the damping matrix and the generalized force vector, and we pass into a new set of coordinates, which is the modal coordinates, only the first three mode shapes. And the nice thing about that is that we obtain a system of three decoupled ordinary differential equations that we're able to solve. We can compute the frequency response functions, we can integrate them, we can do whatever MATLAB allows you to do with them, and we end up obtaining a vector of modal coordinates, which can be complex if we want to compute the frequency response function, which can be a vector of modal coordinates with respect to time if we want to integrate that equation with OD45 to find the time response of your structure, because that is also something you can do with finite element analysis. OD45 is very nice, you can have a look at it, and it's very useful for this kind of thing, but I will show you something which is possible to do with it during the next lecture, so you will also see how to obtain some very funny plots, using the time integration of your system. So in the end, you obtain a response of your system, and then you go back to the physical coordinates by multiplying for the transpose of the phi matrix, which again is rectangular, so we pass from the three modes with which we expressed the displacement of the structure to all the physical coordinates, which are always the same. And the very nice thing about this is that depending on the frequency range you decided to set in your discretization, you can account for some of the mode shapes, not account for others. In this case, remember, we are trying to get the response between an input at mid-span and an output at node 4, so roughly at quarter span, but only considering the first three mode shapes. And if you look at it, we are missing all of them. We're missing all the mode shapes after the third, because we decided to use the language of the mode shape, but only some of them, so we discarded all of them, all the one at higher frequency. And so, due to our simplification, due to our discretization, we decided to we cut out all the values, all the contribution at higher frequency. If you want an analogy, you can look at it like a Fourier transform. If you remember, the Fourier transform was a way of expressing the displacement anytime function as a sum of sines and cosine functions at increasing frequency. Usually, with an ideal discrete Fourier transform, you can completely reconstruct the signal. But if you cut at a certain frequency, if you filter out all the frequency higher than your threshold, you will lose that frequency contribution in your reconstruction, and so you will have a partial, filtered signal out from your inverse Fourier transform. In this case, we are using not the same approach, but with mode shapes. So let's say that you are interested in expressing the displacement of a bridge. Sorry, I'm like using bridges as an example today. Maybe you're not interested in the 11,000 mode shape at 500 Hertz of one of the cables, because that's not something which is interesting for you if you're looking at the value of the lateral displacement of the deck of the bridge at 2 Hertz. So that is an information you can discard. So why the hassle of solving the system of equation with finite element analysis for all those constraints, where you can just go into model coordinates, filter out all the constraints, all the components you are not interested in, and then going back to the physical quantities, losing a little bit of information, but who cares, because we just are interested in a certain frequency range. So the model approach allows you to simplify FEM even more. So from the first part of the analysis, you get the general behavior of the structure. You find all the mode shapes you are interested in, then you cut out all the mode shapes you are not interested in your analysis because you just want to make a specific analysis, but then it's something up to your sensitivity. You pass in other coordinates, you solve the problem, you pass back to physical coordinates, and then you get your structure. So this is again the chain of thoughts that you have to follow to get your response. Of course, you can play with this, and I would suggest you try to see which is the behavior of the structure, changing the number of mode shapes you insert. Let's try using only the first, the second, the first and the second, all of them, and try feeling which are the differences, try seeing which is the effect or the amplitude and the phase in various points where you change how you want to reconstruct your structure. Because actually, in some frequencies, as you can see, below a certain threshold, the reconstruction is perfect, but at higher frequencies, it changes a lot. If you're interested, there was an assignment a couple of years ago where a coherent, a certain number of mode shapes was required even by adding more mode shapes, the structure was not, the response to the structure was changing. After adding the 6th or the 7th one, it was changing completely, because some mode shapes have an influence in some areas of the structure, some mode shapes do not have an influence in some other parts of the area. So it's up to your sensitivity to play a little bit with the parameters of the reconstruction and see what happens. Okay. Last part, and I swear that's the last thing we're going to do today also, because we have 10 minutes, but this is something, is the static deflection. So, right now, we discarded any contribution of gravity or external forces, because we just said the structure is there, is living in its perfect world, there are no external forces due to gravity, due to force field, due to everything. But sometimes you are interested in seeing what happens when you have an external force field applied to your structure. And that force field is constant because, as you know, gravity, for what concerns us, is constant and it's always the same. So maybe you design a structure, you use FEM to compute the response of the structure. But then you want to know which will be the loads applied to the structure by its weight or by the weight of a load which is applied to it. And so you also want to know which is the movement of the structure, because any structure at which you place a load upon changes its shape because it deforms a little bit. To do that, we can use a small trick. We have a lot of tricks using finite analysis, which is the fact that a constant load will result in a constant displacement. So load is not changing, so after settling in, the response of the structure will be constant. I have never seen a bridge moving due to gravity waves. So in a way, we could say that the first derivative of the force of the displacement field due to an external load will be 0, and the second derivative, of course, will be 0, so no acceleration due to shifts in gravity. So we are left with a matrix, which is a stiffness matrix of our system in free coordinates, because remember that the frame coordinates do not move if you apply an external load, and if they move, that's a bigger problem than finite element analysis. So we are just left with a known force vector, which can be an external load about the structure, which can be the own weight of the structure. So you can also try computing which is the structure's own weight. And the unknowns are the transversal, vertical, and rotational displacement of the structure due to an external load. Easy to compute. Force vector multiplied by the inverse of the stiffness matrix. Because the stiffness matrix gives you the elasticity of the structure. So if we give a certain forces around the structure will move, and we can link the movement of the structure to the vector of external forces, also in the study case using the stiffness matrix. So you know, for example, in this vector you could place the weight of the various elements. Of course, remember that you have to compute how the weight of each of the elements transfer to each of the coordinates, but for that we will also go a little more in depth on that in the last lecture. But so you compute the external loads, which again can be cars, can be the integral of any concentrated or distributed load along the length of the structure. You feed it into that force vector, and then you divide or multiply that force vector times the stiffness matrix, and then you get the displacement of all the points on the structure based on its weight, the weight of passengers, the weight of cars, the weight of anything you place on the structure. And after you do this, you can just use the plotting functions we gave you to find which is the general shape, the general arc, in this case, of the structure. Remember, in this case, we are just giving a vertical force going up, so we shall expect the structure to move upwards, because we're just deforming in this direction. If I can give you, this is also something that will be interesting also for your assignment, at least to have a grasp on it. Let's try looking at how to implement the weight of the structure to this formulation, because it's not, you cannot just put a vector which has the weight of each of the elements for each of the coordinates, because remember that some coordinates will be affected by the weight, some others, of course, will not. So you can try thinking about how to implement the static deflection of a structure to its own weight. In any case, next week we are going to see it more thoroughly, so you can try anticipating it, but in case we will also discuss about it together. So you can, if you want, you can come before the class next week. We can discuss about your solutions, and then I will present to you the how to do it version of it. So remember in this case that the results that you get will not be a mode shape, so it's not scaled down by any quantity. So the values displacement you get from that formulation are the actual displacement of the structure, because you're giving to it a certain weight, so we shall expect a certain displacement. So it's not a non-dimensional transfer function, that is a displacement. Okay, so again, exercise for you for the next week. Of course, most welcome to work on it. Of course, most welcome to email me if you have any doubts, any questions, any curiosities you would like to discuss. Same structure of today. We have the various concentrated elements on one side. We also have a force on node 4. And the assignments for you is to find a certain set of transfer functions, to find, of course, and to compute the mass and the stiffness matrix of the structure, and then to go throughout some of the topics we discussed today to be implemented on this structure. You find part, I will upload this immediately, you will find also part of the codes that are necessary for this in the slides of today, so you are most welcome also to copy, paste, and work around your code. You don't have to develop it completely, but let's try looking at this project, at this very small assignment with a critical eye. So let's discuss, remember some of the things we discussed today. Let's try to see what happens if we change the number of mode shapes. So let's see what happens if we change the position where we apply a certain force or the value of the force. And let's try playing a little bit with the code to see which are the effects on the results you get. Okay, that will be all for today. I also will upload some of the results and see you next week, same time frame. Ok, questo lo terminiamo.